Hello everyone, welcome to RISE 2022. I, Shivangi Agarwal, will present our poster Learning Estimates using Intermittent and Age Measurements, which I have done with the other faculty from IIIT Delhi, Dr. Sanjit Kaul, Dr. Saket, Anand, and Dr. P.V. Sujit. Cyberphysical systems have agents which receive measurements of states of other agents of interest and their control commands over a network as update packets. Due to the network resource constraints, these update packets arrive at the estimator, which are intermittent and aged. To compensate, an agent, which we call as the estimator, calculates the estimates of the measurements of the states using the history of update packets received. However, as seen from the state of the art, most of the works on estimation assume knowledge of the dynamical model that governs the measurements. However, assumption of availability of models may not be practical. Also, unlike many other related works, which can be seen here in the state of the art, we allow updates to arrive at the agent, also known as estimator, by calculating the estimates intermittent and be aged on the arrival. Next, I'll talk about the target system, where we have modeled a discrete time dynamical system using the equation xk plus 1, which is a function of the last state, the control, and some noise. The measurement is a function of the last state and the measurement noise. In our work, we assume a model-free setting and detail a novel deep neural network architecture that leverages LSTM to learn estimates using updates received over the communication network. As you can see here in the approximation architecture, the input to our proposed neural architecture is the last known estimate, the very recent received measurement over the network, and their corresponding ages. Now, the interesting point to note here is that age of the update at the estimator will keep increasing and will reset once a new measurement is arrived at the estimator. We finally devise our optimization problem, where we say that consider our theta, which can be said as weights and biases of our proposed architecture that we call as LSTM AA, and a measurement residual, which is the difference of the received measurement and the estimate at any time step t. The estimator wants to minimize over a time horizon t the measurement residual, which is simply the summation of epsilon yt transpose with epsilon yt. We have simulated our architecture and shown the efficacy of our results on the two linear as well as the non-linear dynamic system. For the linear dynamical system, the motion is governed by the Newtonian kinematics, and we estimate current position and velocity. Similarly, for the cart pole, which is simply a pole on a moving cart, and we estimate velocity of cart, angle, and angular velocity of the pole. Next, to consider the network constraint, we simulate our network as a queue, where we say that P is the update arrived at the network with some probability P. Similarly, the Q is the update transmission time, which is being sampled from a geometric distribution. To cover the entire network horizon and to say that we have simulated over a wide horizon of the utilization P by Q, we say that we start with the low rate P 0.01, and then we go on to the age optimum, where the updates arrive on the estimator at the age optimal manner, and then finally we talk in the terms of high rate, where our P are correspondingly 0.01, 0.1, and 0.297 respectively for the Q service rate of 0.3. Briefly describing the training process, at every time step T, we have some measurement YK and some control UK of the target, which goes through the network and arrives at the estimator with some probability Q. Y tilde K and U tilde K is the most recent received measurement update and the control update at the neural architecture, which also takes into account the last calculated estimate along with the age of both the updates. Finally, we always sample the minimum batch size from the replay buffer and then update our LSTM architecture using LSTM A architecture using backpropagation. Finally, going through some of the results that we have shown. This is the first one where the target's known, where the target's control is known, and we know that the time varying Kalman filter is optimal for such kind of condition. Here we can say that our LSTM AA performs almost as well as a time varying Kalman filter. Similarly, then we go on to our next horizon where we say that the target control is unknown and we try to see whether age in the input actually benefits estimation. We try to show the efficacy by comparing it with three different scenarios where we say one of them is where we have the age in the input, the other one is the time varying Kalman filter, and the final is where there is no age in the input. We clearly say that our proposed architecture with age as input does the best, and if we see properly and if you see carefully, the green plot can see that without age as input performs well for age optimality but suffers otherwise. We also talk about another condition where we say that the time synchronization between the target and the estimator is imperfect and unavailable, which we call as the next slide as noisy age estimates. We can see that here we give noisy age only during testing, and we see that the LSTM AA does not suffer in its performance and is robust to the noisy age. However, if we carefully observe the red plot, the TVKF plot, its performance drops compared to when the true age is available. Finally, for a very real life application, it is not always possible to train the different LSTM models or say different estimators for different values of the network. So we try to train over time varying network where we say that we train by choosing P and Q uniformly from this given interval at the start of every episode. But we also compare the efficacy and we also compare the performance with the fixed training, and we see that they almost perform very well, indicating that LSTM AA need not train different models for different networks. Such networks, as correctly said, are more suitable for real-world settings. Concluding, we proposed our deep neural network architecture to learn estimates of state measurements in a model-free setting using intermittent and A-state measurements. Such measurement updates and their age as input to LSTM results in smaller estimation error as correctly seen from the results above. Our model is also robust in the presence of noisy age estimate, and we also show that we need not train different LSTM model for different network configurations. I have added a paper link which is being uploaded on the archive. Interested readers and viewers can please contact me or can visit this link and let me know about more information if required. Thank you so much.